So the three of us are going to be co-presenting this. When there's really, the objectives are to align the research questions to the variables in your statistical analysis. Then to go over power analysis and sample size calculations using the G-Power software. Building a data set using SPSS. Conducting an independent samples t-test and an analysis of variance using SPSS. And finally, interpretation of SPSS output for both the independent sample t-test and the analysis of variance that we're going to run. So again, my name is Dr. Patrick Dunn. To add to my bio, I'm also a proud graduate of Walden University. I graduated with my PhD in public health in 2015. So many of you that are students know that I was on your side of the equation, and thank you for your persistence and diligence in attending programs like this. So we're going to start by going back to the research question. You can't start just with the statistical analysis. You're kind of putting the cart before the horse. So always what you're going to do is first identify what research question am I trying to solve for. And so we're going to do two examples. In this example, is there a difference in cell phone usage for active versus inactive lifestyle? So to answer that question, we really have two major buckets of decisions. One is what variables do we have available to us? And then finally, what statistical analysis or statistical test will we use to answer that research question? So in this case, we have a dependent variable, average monthly minutes. And this is measured in minutes, so it's a scale variable using SPSS. We also have an independent variable or a grouping variable. In this case, it's lifestyle, and there's two groups. So there's active and inactive. So just to see how many of you are actually paying attention, based on the research question and the two variables, does anybody want to guess what statistical test would be the best choice here? Go ahead and just type responses into the chat. Looks like a bunch of people are typing. So while you're typing, so nobody gets put on the spot, we'll go to that. It would be the independent samples t-test. That is the test that you would use if you have a scale variable, dependent variable with two choices. So you're going to be comparing two groups. The next one is there a difference in the cost of phone service by age group? In this case, we have the average monthly bill, and this is in dollars, so this is also a scale variable. And here we have a slightly different independent variable because we have more than two groups. We have age category, and there are 4 groups. Okay, so those of you that know about t-tests know that you can't run a t-test with more than 2 groups. So again, before I click the answer, if anybody wants to take a shot at what statistical test would be the best one here, and the answer to that would be the analysis of variance. Okay, I'm going to turn over to Dr. Jones for the next part of the presentation.
All right, thanks, Pat. Hi, everybody. Matt Jones here. I'm going to talk a little bit about conducting a power analysis for our minimum sample size calculations for the research questions that Pat just went over. And there are many different ways to calculate power, well, many different mechanisms, I should really say, software mechanisms. We're going to be focusing on the G-Power software here. G-Power is a free software download that you can get if you haven't seen it before. You just go ahead and Google or Bing, whatever your search preference is, G-Power will probably be the first thing that comes up and is relatively easy to install. So we're going to be using that for our example today. So as you can see here, we've already gone over our first research question. Is there a difference in cell phone usage for active versus inactive lifestyle? If we were going to perform an analysis to answer this question, we really want to know something about power, and power relates directly to our minimum sample size. So we want to know what is the minimum sample size that I need to have enough power to be able to detect any effect that might exist within the data. And I'm going to talk a little bit more about that if we go ahead and walk through this here. So the output that you're going to see here is a copy and paste from the output from G-Power. So when you run this, you'll be able to see something very similar. So we already know, going from what Pat told us, that we're going to be doing an independent samples t-test to answer research question number 1. And on G-Power, this is under the test family of t-tests. The specific type of test using G-Power language here is means difference between two independent, that part's important, two independent means of two groups. The type of power analysis that we want to do is what we call an a priori. And this will show up just like this: a priori, compute required sample size given an alpha level power and effect size. Those are the three key pieces that we really need to know to get a minimum sample size, or alpha, power, and effect size. Now you can do a post hoc power analysis. I'm not going to talk really much at all about that today, and there's a lot of literature that surrounds that, noting that it's not typically beneficial. You want to focus on the a priori, so that is the beforehand, before you're conducting this analysis. What is the minimum sample size? You always will be asked for tails. So this refers to whether this is going to be a one-tailed or a two-tailed test. And whether that is the case really goes back to how you've stated your hypotheses. So here we have a two-tailed test because we have, or let's assume at least, a non-directional hypothesis. We just want to know, is there a difference in cell phone usage between active versus inactive? We're not stating a one-tailed hypothesis that, I think active is going to be more than inactive. It's just simply, I want to know whether there's a difference, either way, more or less between the groups. So that becomes a two-tailed test. The next critical piece of information we need to enter is the effect size. And there's a small d here, and that refers to Cohen, the famous psychologist / statistician, Cohen's d. And 0.5 is often considered, at least by Cohen's categorization, a medium effect size. Typically, if we know nothing about, if we don't have anything about the effect size, we haven't run a pilot study, we don't have anything in the literature that mentions effect size, what we often want to do is go ahead and assume a medium effect size, that this is what we think is happening out in the population, this is what we think we're going to be able to detect at the medium level. If you play with that a little bit, if you go down and say, okay, I want to be able to see a small effect size, that's going to have a direct implication on your minimum sample size requirements. Your sample size requirements are going to go up. Likewise, if you have a large effect size, they're going to go down. So medium is sort of that middle of the road, if you will. Alpha error probability. So this is referring back to the p-value and specifically your type 1 error. So what, when you enter this, we're thinking about the rejecting the null and error, and we want the probability of that to be fairly small. Likewise, on the opposite side, we can think about type 2 error and power. So power is 1 minus that, and we can play with this number as well. So right here again we have this, what's often considered a conventional minimum threshold, which is 0.80. So we want our studies to be powered at the 0.80 level. Now you can go ahead and increase that threshold, and I think in G-Power actually the default when it comes up is 0.95, which is much higher. So your probability of engaging in type 2 error, of not rejecting the null when you should have, or not being able to detect an effect out there in your data when one does exist, is lowered. So what I would recommend, and I think a lot of my colleagues recommend, is just starting off with that 0.80. Obviously, as you move this number higher, going up to 0.95, let's say the default, again, that's going to have direct implications on your sample size. Your sample size requirements are going to increase. So it's going to spit back a total sample size required much larger if you have that higher power. So if you don't have G-power, where once you do get G-power and you just want to sort of play around with how these numbers work, I think that's a fantastic exercise, seeing how if you increase one, it affects sample size, and decrease another, it affects sample size, and so forth. Okay, the next piece of information we need is the allocation ratio, N1 over N2, and this is specific here to our independent sample t-test. And when we're saying an allocation ratio for N1 to N2 of 1, that's saying we're assuming both groups, the sample sizes for both groups will be exactly equal. Now, in reality, that doesn't happen a lot unless you have a lot of tight controls and you're working, let's say, in a psych lab. But still, you can go ahead and assume that it'll be approximately, and I really want to put emphasis on that word, approximately the same. So assuming there's one, the N1 divided by N2 is 1, sample allocation is 1 for 1 between the two groups, our final, or the answer we're looking for, our final output, is that we need 128 units, whatever they are, whatever it is we're measuring, people, organizations, whatever the unit of analysis is, whatever the case is, we need 128 of those. So as you can see right here, we have 64 and 64, that equals 128 for the total sample size. With an allocation ratio of 1 to 1, there is 64 in each group. It is equally distributed. And that gives us this actual power of 0.80 and some change here. So we entered it as 0.80, and it sort of does some rounding, but tells us, the software tells us, okay, you need, the power calculations it's doing behind the scenes for us, you need a minimum of 128, I'm just going to call them people as subjects for this, but whatever it is that you're measuring, you need 128 people to be able to detect an effect and have sufficient power. This becomes important because sometimes you'll hear about studies that are quote-unquote underpowered, and we're cautious of those if we don't reject the null and they're underpowered. They have a small sample size, and for those of you who are already in the dissertation or capstone phase, maybe your committee's already hitting you with questions about increasing your sample size. This is why we worry, one of the reasons why we worry about sample size. That if a study is underpowered and we didn't find an effect, that we might be, we might be engaging in a type 2 error. That is, we didn't reject the null when we should have. I mean, we don't know if that's the case because it's underpowered. If we have enough sufficient power and we still fail to reject the null, then we can be a little bit more confident that we're not engaging in a type 2 error because that test is sufficiently powered. So that's how we did it for research question 1. Research question 2 is very similar, except there are a few slightly different pieces. So power analysis is conducted just a little differently for each specific statistical test. So when you're asking about minimum sample size related to power, you need to know what statistical test that you are using. So for research question 2, we have, is there a difference in the cost of phone service by age group? We already saw that this is going to be a one-way ANOVA. So moving down here in G-power, this is under the test family of F tests, since the one-way ANOVA gives us a critical value of an F statistic. And specifically in G-power, this will be listed as fixed effects, omnibus, one-way ANOVA, one-way. So sometimes it's just referred to as a global ANOVA, but this is what the language G-power uses. So again, type of power analysis, a priori, so beforehand, compute required sample size given power and effect size. Again, this will be a drop-down menu for you in G-power. This isn't any information that you have to hand enter by typing. From the same drop-down menu, tails, we want this to be a two-tailed test. We don't have any direction to our question or hypothesis. It's non-directional, and that's perfectly fine. For effect size, if we had a Cohen's d for the independent sample t-test, for the one-way ANOVA we have an F, which is a measure of the effect size. Again, assuming a medium effect, that value is 0.25. And for these values for each individual effect size, you can just go ahead and Google those out there. Like, what are the effect size for independent sample t-test, one-way ANOVA, and there's some rough approximations. Going back to Cohen, he did a categorization some years ago, and a lot of people use that. It's in a lot of books, so you can figure out what are the cutoffs between what's considered small, medium, and large. And they're all pretty close to each other. Again, same information as we entered before. You know, our typical alpha error probability of 0.05. I already mentioned the power. You know, at the minimum we want it to be 0.80. So let's just start off with minimum because we're trying to achieve a minimum sample size. Unique to power analysis in ANOVA, because we're dealing with a factor as an independent variable, it has groups, it has levels to it, right? So G-Power asks us, well, how many groups do you have for your factor? Well, as Pat mentioned, we have 4. We know that. We have 4 groups. Okay, so the total power, so the total sample size then is going to be 180. Which gives me that actual power point, again, 0.80 and some change. A priori, before we've run any analysis. So it's important to focus on this total power, this total sample size. You see, before in the independent samples t-test, we talked about the allocation. So here it's just telling us you need a 180 across those 4 groups. Optimally, from an analytical approach, we definitely would like to see equal distribution across those groups, and I'm going to say approximately again. The further we move away from that, the more problems that can arise, and we don't have time to talk about those here. But when it's computing total sample size, it's figuring there's going to be approximate equal distribution across those groups. I'm going to hand it over now to Zin to talk about building this data set in SPSS.
Great, thank you, Matt. What I wanted to discuss today is about building a data set using SPSS based on the research questions and the power analysis presented by both Patrick and Matt here. There are 2 approaches that you can do for building a data set. You can bring in your data first and then develop the variable screen, or what I'm going to show you today is we're going to build actually the variable view first, and then we're going to import in the actual data. It doesn't matter which direction you go. It's just that at the end, you need to come up with, at the same point, is where you have the data view shows all of your data, and then on the variable view of SPSS, it actually has all of your variables laid out for you. So beginning here, we actually see this is the variable view of a new data set, and we know that we're in the variable view because in the lower left-hand corner of the screen, you'll see that there's the variable view tab is highlighted in yellow. We begin by the first column for our first variable, which is going to be that cell, name, and row 1. And what I suggest to students is try to select names that are easy. Many times I see data sets where there's a lot of different codes put in place, and it's difficult to remember what the codes actually mean, especially if you have 40 or 50 different variables. So it's always good to have an easy name to remember. And in this case, what we're going to do is put in age category as we had once before. Once we put in age category, there are a number of columns here in the data set which you can go ahead and play with, but the 3 that I'm going to focus on are actually name, the values column, which is in the middle, and then also the measure at the end. So we put in age category first, and it comes up as a numeric variable. The default from SPSS is a width of 8, and then the decimal places are 2. You can, of course, adjust those as you need. Now, we know that age category is actually an ordinal measure. So when we go to the far right under the measures column, we use the drop-down menu, and we'll change it to ordinal. And then we're going to take a look at the values column, where currently it shows that it's none, which is highlighted in yellow. If we click on the right-hand side of the cell where it says values and none, we'll get a new menu that opens up. A little window opens up in the center. One thing nice about SPSS is if the windows that open up are too small to read, you can use your mouse and grab the corner or the sides and just drag them to be a little bit larger. To go ahead and put in the value labels, under the values box, which is the top rectangular box, I'm going to put in the code of 1, and under the label, I'm going to type in under 31. I'm going to repeat that with the value of 2, and my age category is going to be 31 to 45. Repeat that with value 3, and the label is going to be 45 to 60, and repeat that with the value of 4, which is over 60. Each time you put in the value and then the value is labeled, there'll be a radial button that highlights that says Add. You can just go ahead and add. If you should happen to make a mistake, you can click on the actual values label and then select Change or Remove, and then make whatever adjustments you need. Once it's finished, you go ahead and click the OK button. So now we have our first variable put in place. So we can see that the name is age category. We know it's a numeric. I've changed the width down to 4. The values label, we've put in the values label, and we know that the measure is ordinal. I'll go ahead and repeat that with our next variable, which is active. Now at this time, active we know is nominal because we have two groups that are not, they're either active or not active, similar to what we have in terms of gender. There's no sequence to this. There's just two separate categories. Once again, the values column, it's under none, but we can go ahead and click on the right-hand side of that cell. And when we do that, we'll put in our values. We're going to essentially dummy code 0 equaling inactive, and then 1 equaling active. One thing that I want to emphasize here is when you put in these value labels, these labels will actually show up in the output of SPSS. If you leave these value labels blank, all that's going to appear in SPSS are the actual dummy code numerical values, which are going to be, in this case, 0 and 1, or previously it'll be 1, 2, 3, or 4. So it makes interpretation a bit difficult if you're just looking at pure numbers. That's why I strongly emphasize and recommend that you fill in the blanks here, so that way when you get to your output, it'll be much more easy to interpret. We're going to go ahead and click OK, and then we've got our third variable that we put in, right? We've got minutes, which is our average monthly minutes bill. That's a scale. And then we also have our fourth variable, which is bill, which is our average monthly bill, which is also a scale. Since both of these variables are scales, there's no need to fill in the values column. We already know that minutes is a scale variable in terms of minutes, and bill is a scale variable in terms of dollars. So now, if we switch over to the data view, and you can see we're in data view because in the lower left-hand corner, the data view tab is highlighted in yellow. We can see that our variable names and our measures are in the top row there. We've got age category, active, minutes, and bill. As I was saying earlier, I'm going to import in the actual data values now. I've got them on a separate Excel spreadsheet. However you keep your data, or however you receive your data, it could be an Excel spreadsheet, it could be in a Word document. You can go ahead and copy and paste it in. I'm just going to go ahead and do that now. So we fill in our age category. Next we have our active category. Then we have our minutes, and then we have our bill. Now, what's important, one thing I do emphasize is when you're working on a large data set, is to go ahead and continuously save the files as you move along. If you're working on a data set over a period of time, some of these data sets that we have students are working with have thousands of cases. I strongly suggest that you save the data sets with unique file names. Add in the date, add in a letter after the date, and the reason being is that as you go through and you start manipulating and working with your data sets, you'll have earlier iterations to go back to in the event that you should make an error somewhere along the way. So you might realize that, oh, you know, yesterday I actually put this one in and I shouldn't have. Now I can go back to the previous version where I had all of my data, and then keep moving forward from there. Okay, and at this point, I'm going to hand it over to Dr. Patrick Dunn to show you how to do the analysis.
Great, thanks, Zin. Okay, so now we're ready to actually run the test. So we're going to start with the independent sample t-test using SPSS. So you're going to start in the Analyze menu item up here on the top. So click on Analyze. That'll take you to a menu configuration. So the first level is Compare Means, and then to the right of that you'll see some additional choices. So you're going to select the Independent Samples t-test. Note that there are other types of t-tests, and the one-way ANOVA is also in this group. Once you select the independent sample t-test, on the left you're going to have a list of your variables, and your dependent variable is going to be placed in the test variables. It can be a little confusing with SPSS sometimes because they don't always use the same naming conventions that we're using. So where it says test variables, that would be the same as the dependent variable. So you're going to put the monthly minutes in there. And then your independent variable is going to be in the what's called grouping variables box on the bottom. And note that once you put it in there, you're still not done. There's still some question marks. And that's in this list, this dialog that will come up. It'll ask you, you have two groups, group 1 and group 2. It's going to ask you, what are those groups? So if you actually look behind the dialog box, you can see, and you can know from Zin's presentation, that when you built the data set, you coded those variables as 0 and 1. So group 1 is a 0, and group 2 is a 1. So be sure to put those in there in that grouping variable, and then you'll select continue. And once you do that, you'll click OK, and you'll get your SPSS output. If you've been using prior versions of SPSS, you'll note that the default output now looks at least a little bit more like APA formatted output, which is very nice. But the results are the same, even if you get one that looks a little bit more boxy with the output. The numbers in the boxes will be the same. The math has not changed. So I'm not going to go over the results. We're going to let Dr. Jones do that in a moment here, but this is how we get the output stage for the independent sample t-test. Next, we're going to do the same procedure for the one-way analysis of variance. And you're going to start in the same place. You're going to go to the analyze option. You're going to select compare means, and then the one on the bottom is the one-way ANOVA. You're going to select that. And your dialog looks very similar. So instead of test variables, now the top box, the dependent variable, says dependent list. Again, that would be your dependent variable. So we're going to put the average monthly minutes in that box. And your factor is your independent variable, and that's our age categories. Once you've done that, you've got a couple more selections to make. The boxes over on the far right is where we're going to be focused. So you're going to, just to go back to that, you're going to select the post hoc box there. And you can see that there's a number of post hoc tests available. In this example, we're going to choose the Tukey post hoc test. And then you're also going to click on the Options tab, and you're going to select the Homogeneity of Variance Test box. And once you've done that, you now have your SPS output for the analysis of variance test. I'm going to turn it to Dr. Jones now, and he's going to explain how to interpret those results.
Yeah, thanks, Pat. So this is always the fun stuff. What does all the stuff that comes out of the test mean, and how do you interpret that? So here we have our results from our independent samples t-test. So you can look up here right away. It gives us some descriptive statistics. I think these are always useful. So we have our two groups here that we're looking at and our dependent variable, so average monthly minutes in the lifestyle inactive versus active. We have the actual sample size that was used to calculate that. Descriptives around mean, standard deviation, and the standard error of the mean. So moving down to the actual t-test, that's down here. You'll see in an independent samples t-test, you'll have two rows. Equal variances assumed and equal variances not assumed. And this really confuses a lot of people who are new to t-test and new to reading output, because you need to know which row to read. Now more often than not, the results are going to be quite similar, but sometimes there's just just enough difference to make a really big difference in how you're interpreting your output. Specifically, are you going to reject the null or not? And you can kind of see that from this example here in just a second when we're going to talk about what the p-value ended up being here. So the first thing to determine which row to read, we really need to pay attention to this first section of the output. And this is the Levine's test for equality of variances. So that tells us read the bottom row or the top row. And simply it's just asking a question, between the two groups, are the variances equal or not? So is the spread of data equal or not? And it tests the null hypothesis around that. So here we want to look at our p-value, which is labeled as, abbreviated as SIG, S-I-G, in SPSS. And you can see that we have a fairly low p-value, so 0.033, which is well below the conventional and arbitrary cutoff of 0.05. So what we can take away from that is we want to reject the null that the variances are equal. Therefore, if we're rejecting the null that they're equal, we are assuming that variances are not equal. Okay, so that tells us we just need to follow this bottom row here. Equal variances are not assumed. You see a critical t statistic for both, whether we're looking at the top or bottom, is very similar, and our associated significance, our p-value, two-tailed, is very similar, 0.056 versus 0.053. But this is a good example because this is very close to the 0.05 threshold, and you can see where there might be circumstances, depending on which row you read, it could make a big difference of whether your p-value is going to be 0.048 or whether it's going to be 0.053. Which brings up the question for us today, if we a priori set our alpha level to be 0.050 and below to reject the null, then that means here that we are above, although it be ever so slightly at 0.053, we are just slightly above that. We still would not reject the null. So we would fail to reject the null because we said beforehand, I'm not going to reject the null unless that p-value is at 0.050 or below. And since it's just barely above, I have to stick to what I said, and I'm going to fail to reject the null. Therefore, the null stands. The null that there is no difference between these two groups. Now, sometimes you will see language like, it was rapidly approaching statistical significance, or it was very close to statistical significance, and that's your call whether you want to use that or not. This is just a really interesting example, and I've run across this, and you might at some date in the future where you're doing your analysis, and it's just so close that you're going to have to make that judgment call of whether you think you want to reject the null or not. Either way, it's always important to report exact p-values so that your audience understands when you say you're rejecting or failing to reject, and you report that exact p-value, they know that probability level that you were dealing with. For our one-way ANOVA, I know there's a lot of output here on the screen, and it's kind of too small. But the main thing I really focus on here when looking at the ANOVA here is, first of all, it gives us a test of the homogeneity of variances. And we see the Levine's statistic there is a little bit low, and the significance, it's not significant. And that becomes important because if we did have a significant omnibus ANOVA, we want to make sure that we're using the appropriate post hoc test to do all those pairwise differences, to test all those pairwise differences across the 4 levels of our factor. There are multiple tests for equal variances assumed and multiple tests not assumed. But it becomes a little bit of a non-issue for us here in this output because right away from this first piece of output where it just is labeled ANOVA, that's our omnibus ANOVA. That's the global ANOVA. And we have a p-value going all the way over here to the SIG column, a p-value of 0.094, which is fairly well above our 0.05 if that's the alpha you're choosing. But again, that's the conventional level. It's fairly well above that 0.05. So right away we know, at least at that level, at the 0.05 level, that there are no differences in the data. So really there's no need to do any post hoc test unless you want to do a little bit of further investigation. There are times where some odd things can show up, and it might be worth your time looking at the multiple comparisons just to do some double checking. But typically, if you see a global one-way ANOVA that is not significant, you're done right there. But we can verify this here looking at our multiple comparisons. And again, this tests all the pairwise comparisons across our factors. So the age group of under 31 to 31 to 45, the group of under 31 to 46 and 60. So again, all possible pairwise combinations. And you can see that we do not have, just moving down the significance column here, you can see that we do not have a p-value that falls below that 0.050 level. Therefore, there are no significant differences. And when I'm saying significant, I'm talking about statistically significant differences, and the null in this case would stand. The null that there are no differences. Okay, I know we went through a lot of material here rather quickly, so I guess the three of us are happy to open it up for questions. So I see the first question is, how do you create a subgroup in SPSS? I know, Zin, you went over sort of creating structure in data sets, and I know this is something you like. Do you want to give that a try?
Sure. I'll go ahead. To create the subgroups in SPSS, you basically have all of your cases, and say for instance, if we're looking at people, and we have 1,000 people, and one of our subgroups is going to be ethnicity, then you want to create a variable for ethnicity, and then fill in the values column which each of the dummy codes relates to which ethnicity. Once you have that built, you'll want to actually remember to put in the nominal measure as well. Once you have that built, you'll have the subgroups there. And in SPSS, if you wanted to say, for instance, just look at African Americans, you can use the select cases function, which is part of SPSS. Select where ethnicity, the code for ethnicity equals, say, 3. And by doing that, SPSS will isolate out just the dummy code equals 3, and then you can work with your group that way. I hope that answers your question.
Yeah, and I see Pat has already typed in the question for Evelyn, but just if I add 2 cents, I'm not sure I add any value here to it, but when you're doing mixed methods analysis, since mixed methods has a qualitative component and a quantitative component, then theoretically that you would need software packages for both a quantitative like SPSS or R, or another quantitative package, and then for your qualitative piece of the analysis, you might need a qualitative package like in vivo or Atlas TI, or maybe you're doing it by some hand coding. So those, in mixed methods analysis, that's a case where you would need 2 packages.
There's a question about in vivo. I don't believe in vivo is available through Walden in the same manner that SPSS is available.
Yeah, so we do not offer, so as Sean's saying, it is not, we do not offer availability to a qualitative software package that I'm aware of, at least. But there are, for those of you who are interested in qualitative research, there are a number of open source, that means free, qualitative software packages that are out there. I have had some of my own students use them in their dissertation research.
There's a question about G-Power. I believe G-Power is a free download. I saw earlier in the chat where there was a price associated. Unless something's changed, I do believe you can download G-Power for free. Just Google, just put in G-Power, and you should get the link.
Yeah, Pat. Last time I checked, it was for free as well. I certainly downloaded it for free, And I'm just on the web page right now, and bullet point number 1 under download is G-Power is free for everyone. So that's good news. And I see there's a question of whether we have a list of open source qualitative packages. No, I do not think so, but there really are not that many, to be honest. So if you just spend just a very little bit of time on the web, I think you'd be able to find them. I'm thinking of one specifically. I think it's called Hyper Research or Hypertext or something like that, which is a popular open source one.
And some of the qualitative packages also have student options. I know I used one, I just got the student version, so it was much less expensive than the full version. Mm-hmm. It was called MaxQDA.
Yeah, and just to follow up, I believe that package, the qualitative one I was talking about, is called Hyper Research.
You know, one thing I just wanted to add about G-Power is there's, I'm going to post a website here, a web link. G-Power is really quite, you can do quite a lot with it, and sometimes it's difficult trying to find instructions on how to actually use G-Power for any particular statistical tests that you're running today. You know, we use the example of independent sample t-test and the ANOVA, which are fairly straightforward, but if you're looking to do, say, for instance, binary logistic regression or ordinal logistic regression, or perhaps even chi-square, this website that I just posted the link to actually offers it's a pretty good resource. You pick the test that you want, and then you scroll down, and it's a good explanation of what values you need to put in and where, because not all of them are always so straightforward, and you know, there are some, I think there's some 60 different statistical tests that actually can be run through G-Power for calculating minimum sample size or achieved power or achieved effect size and such.
Yeah, thanks, Zin. And just, I mean, for power analysis, it can be very confusing. So if you're feeling a little bit lost and this is your first exposure, even if you've had multiple exposures to it, don't feel bad. It confuses the best of people. So just remember there are two key things we're focused on in hypothesis testing, type 1 and type 2 errors. So when we're thinking about alpha is the probability of our type 1 error of a test incorrectly claiming any statistical significance. And then we have beta, which is the probability of the type 2 error. So in any specific hypothesis, we incorrectly conclude there is no statistical significance. The null remains. And power is that 1 minus beta being the probability of type 2 error. So that's that 0.80 value that we entered into G-Power.
The question about software for mixed methods research, my advice is it probably depends on the type of statistical or quantitative analysis that you're planning to use.
Unlock your device.
Statistics you really can't do by hand. You're going to need a software program for them. Whereas the majority of qualitative research you can do without a statistical or without a qualitative software package.
Thank you for attending this presentation, and I'll close the session in about 5 minutes.